All right, so the topic for today is stacks. So we'll talk about what they are, and we'll talk about how to use them, what they're good for. So we first have to talk about the idea of an abstract data type, an ADT. So an ADT is a model of a data structure that specifies some things. It specifies the type of data that is being stored. It specifies the operations that are supported on that data. And we call these operations methods in Java. And then in addition, the ADT specifies the parameter types of the operations. Wehowever, the ADT specifies what each operation does, but not how it does it. Okay, so we're going to be we try to make a clear differentiation between the specification of a data structure, by specifying what each operation of the data structure does, from the implementation of the data structure, meaning how to do each operation, how each operation is implemented in code. So in Java, an ADT can be expressed by an interface. You'll recall, hopefully, that an interface cannot be instantiated. So you cannot actually create an object of an interface. So an interface doesn't exist. An interface doesn't have code that you can just run. You can just instantiate and run, typically. And by default, its methods are abstract. So this is perfect for an ADT, because in an ADT, we want to be able to write method headers. We want to specify the operations that can be done without having to implement those operations, which is perfect, which is perfectly accomplished using abstract methods. Okay, and then now an ADT, if we just have an ADT, that's not really enough, because we cannot create an object of an interface, right? We cannot instantiate an interface, and so we couldn't really use any data structure if all we had was an interface. So we say that an ADT is realized by a concrete data structure. In Java, this is modeled by a concrete class that implements the ADT's interface. A concrete means non-abstract. So we have a non-abstract class that implements the ADT's interface, and that is a realization of the ADT. Or you can also say it is an implementation of the ADT. Now, unlike interfaces, concrete classes must specify how the operations are performed in the body of each method. And so the ADT, the interface, gives us the method headers, gives us the types of operations that are supported and the parameter types, but then the class gives us the method bodies, or the implementation or the realization of the ADT. So we're gonna use this concept of ADT when talking about stacks and when talking about other types of data structures. So one type of ADT is the stack ADT. So what is a stack all about? Well, a stack is a collection of objects that are inserted and removed according to the last in, first out principle. All right, so the basic idea is you can add something to the stack, you can remove something from the stack, but it has to follow the last in, first out principle, or LIFO principle. What does this mean? So what it means is that a user may insert objects into a stack at any time, but may only access or remove the most recently inserted object that remains. And that's the last in, the most recent object that was added is the first out. Okay, so here's a classic analogy: a stack of plates in a spring-loaded dispenser. Okay, so imagine you have in a cafeteria, say, you have a stack of plates or a stack of trays in a spring-loaded dispenser. So there's a dispenser, and on the bottom there's a spring, and you have the stack of plates there. So when we need a new plate from the dispenser, we pop the top plate off the stack, and that's the terminology we're going to use: pop. Okay, so here's an illustration from a website. So you have a stack of plates. There's a spring on the bottom. When you want to take a plate off the stack, when you need a new plate, you pop it off the top. When we want to add a plate to the stack, right? When we have, let's say, when we're done with the tray and it's washed out, or done with the plate and it's washed out, and now we put it back onto the stack, we push it down onto the stack. So the terminology here that we're going to use is push. We push it down on the stack to become the new top plate. And this looks like this, right? You take this new plate and you push it onto the top of the stack. So you can just, all you can do with the stack basically is pop things off the top and push things onto the top. And the idea is that the plate, when you pop off a plate, the plate that gets popped off is the most recently added plate that's available on the stack. So let's give a specification of the stack ADT. So first we specify what type of data the stack stores. Well, the type of data that the stack stores is any type of data. Stack is a generic type. So we're going to use generics to implement for the stack interface, and then for any implementations of that interface, we will also make them generic so that stacks can work with any data type. Now, we're going to talk about the operations that a stack has. We're going to divide them into two parts. The two fundamental operations are the ones we saw on the previous slide: push and pop. Okay, so push E. So the name of the operation is push. It takes an element it takes E. So, and I didn't specify the type here. I should have, but anyways, let me do that. All right, so the push method, the push operation takes an element of type E. E is the type parameter that we're going to define for the stack type. And so the push operation, or the push method, adds element E to the top of the stack. The pop operation removes and returns the top element from the stack, or it returns null if the stack is empty. So those are our two fundamental operations. They correspond to the illustrations on the previous slide. Now, there are also additional operations, which are not absolutely necessary, but they make using a stack more easy. They make it more convenient. You can call these convenience operations. Peek, size, and is empty. All right, so peek returns the top element of the stack without removing it. Okay, so it's very similar to pop, but pop, when you call pop, it removes the element and returns it to you. With peek, it just returns it to you, but it doesn't remove it. Now, what about if the stack is empty? So then this method returns null. Then there's another method called size that returns the number of elements in the stack. And is empty it returns a Boolean indicating whether the stack is empty. So let's see some code that shows how to use a stack using these operations that we talked about, and then we'll see how to implement it. Here we have a very tiny, simple class named plate. And we assume every plate has an ID number, and there's a constructor that takes an ID number and assigns it to the field. And then there's a toString method that returns the word plate, followed by the ID. Okay, now let's see how we can use a stack. So here we are going to say stack of plate. Remember, a stack can hold any type of data, so including plates. Stack of plate, called plate stack, equals new. Now here we might want to say new stack, right? We might want to say new stack, but the problem is that stack is going to be stack is the name of an interface. Stack is the name of an abstract data type, which cannot be instantiated. We cannot create an object of the stack interface. So we have a class, which we're going to see soon, but we have a class named link stack, and I'll just show you the header of the class. Okay, so the header of link stack implements the stack interface. So we can create a new link stack and use a stack variable, of type stack, to refer to that link list. Sorry, to refer to that link stack, rather. Okay, again, so we are creating something called plate stack, which is of type stack of plate. And the actual type of object that we're using is an object of the link stack class. And the link stack class implements the stack interface. All right, then we can push a plate onto the stack. So we can say plate stack.push and pass in a new plate and push another plate and push another plate. And then we can go ahead and print out the plate stack. So let's see what we have. All right, so let's take a look. So here we have, when we print out the plate stack, we have this. It says the word top and the word bottom, okay? And in between we have the stack. So this is, the words are just indicating what's on top, where's the top and where's the bottom of the stack, because this is being printed on the screen from left to right. And so, you know, we could have potentially printed it in either direction, with the top being on the right or the top being on the left. Here we chose to print it with the top on the left, and we can see that the top element is 300. Why? Because that's the most recently added plate. The next element under the top is 200, plate 200, and that's because that was the element that was added right before 300. And then at the bottom of the stack, we have 100 because that was the first element that was added. Okay, so that's this line of output was the result of line 21 in the code. Then we can say plate stack.peek, and what that gives us is it gives us access to the top element of the stack. It tells us what's at the top of the stack without removing it, though. So we have plate 300. Then we once again go ahead and print out the stack just to show you that the stack has not been changed. Nothing has been removed yet. So here we still have the same stack. And we say plate stack.pop. So here we are removing an element, but the pop method not only removes the element, but also returns it to us. And here is that element that it returns to us, the top of the stack, right? So it pops the top plate off. And then now when we print out the plate stack again, we see that plate 300 is gone. It has been popped off the stack. All right, let's keep going. So here we can push another plate onto the stack. And now if we go ahead and pop something off the stack, it's going to pop the most recently added. Actually, let me rerun it. Okay, so we were over here, right, where we just added a new plate. And so now we print out the plate stack. Yes, here we have our new plate, plate 50, that was just added on top of 200. So 200 was there before, and 100 was underneath that at the bottom. And now we can, pop things off the stack again. So, or we could have always popped things off the stack, but whatever. We do plate stack.pop and pop this plate off. Plate stack.pop. So we first pop plate 50 off. That's at the top. Then we pop the next thing off, which is plate 200. And then we pop the next thing off, which is plate 100. And now if I print out the stack, okay, I see that the stack is empty. I mean, here's the top, here's the bottom, but the actual stack is empty. Okay, so that is one example of using a stack. Here's another example. So we have stack of integer. So we can have a stack of integers named stack equals new link stack. And here we have a for loop that goes through the integers 5 up to but not including 10, so 5 through 9. And for each integer, it does stack.push I, and we just print a message saying pushing I. Okay, so let's take a look. So we are saying pushing 5. All right, so first I is 5, then I is 6, then I is 7, then I is 8, then I is 9, and then I becomes 10, but then the condition fails, so we don't push 10 onto the stack. And now if we go ahead and print out the stack, we see here 9 is all the way at the top, and that's because that was the most recently added element. Underneath that is 8, because that was the element that was added right before 9, and then 7, because that was added before 8, and 6, and then 5 all the way at the bottom. 5 was the very first element that we added. Then we can push another element. We can say pushing 7 and push 7 onto the top of the stack. And then when we print out the stack, we see that now there's the 7 here at the top of the stack. And you might notice that a stack is allowed to contain duplicate elements. So there's 7 here and 7 here as well. If we say stack.peak, we are given the top element, which is 7, but the 7 is still not removed. So if we print out the stack again, we see we have the same elements. Now, if we pop the top element off the stack, we get 7, but it's also been removed. So if we print out the stack again, you see that the 7 has been removed from the top of the stack. The top element has been removed, but this other 7 is still here because it's not at the top. Well, anyways, we popped off this element, not this one, right? We popped off the top element. Now we can also get the size of the stack if we want. So we can say stack.size is 5, right? And that makes sense. 1, 2, 3, 4, 5. Currently 5 elements on the stack. Then here we have a while loop, while not stack.isEmpty, meaning until the stack becomes empty, print out stack.pop. So here we have stack.pop 9. We're popping off 9 because that's the top. Then we pop off 8. That's underneath 9. Then we pop off 7. And then we pop off 6 from here. And then we pop off 5. That's all the way at the bottom. And at this point, the stack becomes empty. And so this condition fails. And so we stop looping. And now when we print out the stack again, we have just an empty stack. All right, so to see one application of stacks, I've gone here to a web page, here the main page of Wikipedia, but any web page would do. And when you're working in a browser, you're at some page, you can go to another page, for example, by clicking on a link. So here you can, maybe I want to read about these battle cruisers and, reading about them. And then maybe I want to read more about, I don't know, something here. Let's see. I want to read about maybe this battle. And, and then after I'm reading, and while I'm reading about this, I want to click somewhere else to want to read about, more about, I don't know, maybe Japanese history. And then reading, and then, so this is, going down the rabbit hole here. And, but sometimes I want to go back, right? So I want to go back. So I can click this arrow to go back, okay? But I'm not just able to go back to the most recent page. I can go back also to the page before that. And the page before that, right? So what's going on here is that there is some sort of stack being stored of all the pages, of all the URLs that I have visited. And if I want to go back to any earlier page, I just pop off the current URL off the top of the stack, and I go back to the one underneath. And anyways, so this is one application of stacks. So internet web browsers store the addresses of recently visited sites on a stack. Each time a user visits a new site, that site's address is pushed onto the stack of addresses. The browser then allows the user to pop back to previously visited sites using the back button. Right now, this is not necessarily how it is implemented in most browsers, but this is one way it can be implemented. Here's another application of stacks. So text editors, right, like your IDEs or even more basic text editors, usually allow an undo operation, an undo mechanism that cancels recent editing operations and reverts to former states of a document, right? So you're typing something and then you want to go back, and then you want to go back. So you can keep undoing, you can keep going back. And this undo operation can be accomplished by keeping text changes in a stack, right? So you keep a stack of every change the user makes, and each time the user makes a change, you pop that change on. Sorry, you push that change onto the top of the stack. And if the user wants to go back to an earlier version, you just pop the current change off the top of the stack and go back to the previous version. And if the user wants to go back further, the user can pop off another level off the stack, and so on. Okay, now we have to now write some code first to specify a stack ADT, and then to implement it using a class or classes. So first we're going to write a stack interface. I mean, it's already been written, but I'm first going to show you a stack interface, and that's going to represent our ADT, our stack ADT, our abstract idea of what a stack is and what operations it offers. And then we'll go on to implementing it with a class or classes. So let's take a look at the code here. Here we have an interface. Okay, interface named stack. It's a generic interface, stack of E. So it can store any type of elements, as long as they're not primitive elements, but any reference type, including integer, including character, right? For to store characters, including plate, any type, any reference type. All right, so we have a few methods here. So we have int size. Now recall in an interface, all methods are by default abstract and public, right? So I could say, public abstract in size, but it's not actually necessary. And you see the IDE is putting it in gray, which is a way of saying it's not necessary. It's not really doing anything. The message says modifier public is redundant for interface members, and right. So in other words, by default, everything in interface is public. By default, everything in interface is abstract. There are ways to make non-abstract methods in interfaces, but for that you have to use special keywords. Anyways, this size method is automatically a public method and an abstract method. And the point of this method is to return the number of elements in the stack. Now, how is it implemented? We don't know. We don't specify that in the stack. The stack is just about telling us what operations we have, not how to do them, not how they are implemented. Okay, another operation is named isEmpty. It tests whether the stack is empty. And it returns true if the stack is empty, false otherwise. It's a Boolean method. Here we have a push method that takes an element of type E and inserts an element at the top of the stack. E is the element that we want to insert. Here we have a method named peek that returns but does not remove the element at the top of the stack. And this method returns the top element of the stack, or null if the stack is empty. So notice the return type is E. A similar method, pop, removes and returns the top element from the stack. Okay, so now, again, we cannot just go ahead and create an object of this interface because you cannot instantiate an interface. So what we need to do is write a class that implements this interface, and then we will be able to create objects of the class and use those objects. So we're going to provide two different implementations of this stack interface. One is going to be this array stack. So you see public class array stack of E implements stack of E. And then another one will be linked stack. So you see public class linked stack also implements stack of E. So we don't really need both implementations, but each of them is nice in different ways. And so let's first take a look at array stack. So the basic difference between array stack and linked stack is how we store the elements, or do we store the elements in an array or do we store the elements in a linked list? So an array stack represents a stack and it stores the elements in an array. So you see private eArray named data. This is a generic array for storing the elements. Now, when we have an array has a fixed size, meaning when we create an array, we have to give it a size, and that's going to be the size of the array for the entire lifetime of that array object. And so now we're going to let the user specify what they want the capacity of the stack to be. Because, so in other words, we're going to let the user here, first of all, we're going to take a closer look at this constructor in a few minutes. But first, let's just say that we're going to let the user specify the capacity of the array. So when the user constructs an empty stack, we're going to let the user specify the capacity. And right now, this capacity means the length of the underlying array. So in other words, the length of this data array. Now, what if the user doesn't want to have to specify the capacity? Well, then we have this other constructor here that takes no parameters and just calls the second constructor with something called default capacity. So in other words, this constructs an empty stack using the default array capacity. So what is that? So this is the default capacity is defined as a static final field named default capacity, which is 1,000. Okay, so it's a final field, so there's no harm in making it public, although we really could make it private. It's kind of up to us. It's a static field because we don't need an individual copy of this data for each array stack. It's just one thing that the class needs to remember. What's the default capacity? It's final so that the user, even though it's public, the user cannot modify it. And it's an int, and it's 1,000. Okay, so again, we have this default capacity field, but we also allow the user to specify the capacity. We have an array of type E named data. We haven't yet created the array, but we've declared it. And then we have this field named index of top. So if we're going to be storing elements in an array, the key thing to realize is that the array might be much larger than the number of elements we have. We may only have like 10 elements on the stack, but we may have an array of 1,000 elements. And so we don't want to have to deal with the entire array whenever we talk about the stack. We only want to deal with the first few elements of the array, right? So for example, if the stack is currently storing 10 elements, we only want to deal with the first 10 elements of the array. To help us do this, we're going to store a variable named index of top. It's an int, and the let me actually just not specify its value yet. Let me do that in the constructor. Let me say index of top is assigned -1. Okay, so the point is that this will tell us the index of the top element in the stack. And it's a private field. The user doesn't have to deal with this directly. The user doesn't even have to know that this exists. This is just going to be used internally in the class to help us access the top of the stack, or to add something to the top of the stack, or to remove something from the top of the stack. We need to know which index the top of the stack is at. And that's what this will tell us. Okay, so let's take now a closer look at this constructor here. So this constructor gets an integer capacity, which is provided by the user. So for example, here we have a main method to test the stack. It demonstrates a sample usage of a stack. And here we say stack of integer stack equals new array stack. But we can also, if we want to, pass in a capacity here. So if we know we want to have a capacity of 10, we can just pass it in. If we don't know what the capacity is and we just want to use the default capacity, we can just call it like this, passing in no parameters. And so anyways, here we have either way, even if we call the first constructor, we end up in the second constructor because we use this keyword to call the other constructor. So we always end up here when we create an array stack. And so what's the first thing we have to do? Well, the first thing we have to do is create this array. Right? We've declared this variable named data, but we haven't created an array object yet. Now, what I really want to do is say something like this. What I really want to do is say data equals new E array of length capacity. Right? That's really what I want to do. But unfortunately, because of the way generics work in Java, you cannot create an array of a generic type. So you get the message here, type parameter E cannot be instantiated directly. Also, by the way, for that same reason, you can say something like new E. Okay. And the reason is that at runtime, E doesn't really exist. E is replaced, E is erased. It's called erasure. Anyways, we don't really need to know these details now. But the bottom line is that we cannot create an array of E. Okay, so what can we do instead? Well, the standard approach is as follows. You create a new array of object. That's legal. Object is the name of a class. It's the class that is the root of the entire class hierarchy in Java, right? So every class inherits from the object class, but you can create an array of type object. So you say new object array with the length of capacity, and then we take this array of objects and cast the array to E array. So we're casting from object array to E array, and you're allowed to cast to the E array type. You're allowed to take an array of object and cast it to the array of E type. Now, one issue is that when I do this, the compiler may generate a warning, not an error though, but a warning. And the warning would say something like, well, let me show you. So let me comment out this line, and here it's gonna say, unchecked cast. In other words, the compiler is concerned that it's, how can we be sure that this cast will be successful? So the compiler may give you a warning. You can ignore the warning because it's not an error. And although in general warnings should not be ignored, this is one of the cases where it is okay to ignore a warning. And it's just a fact of life in Java that when you cast an array of object to an array of E, you get a warning. But there is actually a way to suppress the warning, to make it so that the compiler ignores this issue, and that is using the @suppress warnings annotation and passing in the string unchecked. Okay, you don't really need to know this, but it is a little feature in Java. You may have seen other annotations before. You may have seen the @override annotation. Basic idea of annotations in Java is it's a message to in this case, to the compiler. Just like @override is a message to the compiler indicating that one method overrides a method of a super, that a method overrides a method. I'm sorry. This @override annotation is a message to the compiler that this method overrides a method from a super type, from a super class or a super interface. So suppress warnings is a different message to the compiler, and it's saying to ignore any unchecked type of warnings that might come about as a result of this constructor. Okay, now you don't really have to do this, and you don't really have to understand what's going on here exactly. The main idea is we're creating an array of object, casting it to type E, because we cannot create an array of type E directly. Okay, additionally, we have to say index of top equals -1. Why do we do this? Well, we're constructing now an empty stack, right? It's a stack that has an array of elements, but the stack itself, we haven't put anything into the stack. So the stack is empty. So the index of the top element we'll say is -1. We'll use that to indicate that the stack is empty. It would not be a good idea to say index of top equals 0, because that would mean that there is a single element in the stack and it is at index 0. Right? Because 0 is a valid index. So if I'm talking about index of top equals 0, that means there is a valid index 0, which is the index of top. But so that's not exactly what I want. What I want is an empty stack. I want to represent an empty stack. So I'll say index of top equals -1, which is never a valid index. And so this will represent an empty stack. Okay, Now how do we get the number of elements in the stack? So here we have public int size, and we return the index of top plus 1. So the index of top always stores the top element, the index of the top element in the stack. So for example, let's just draw a little picture. So let's say here we have our array, a very long array, maybe it contains maybe 1,000 elements, or maybe even more. The user can specify any capacity they want. So let's say we have indexes 0, 1, 2, 3, 4, and so on. And suppose this is the stack of integers, and the user has pushed the following elements onto the stack, say 33, 44, and 55. Okay, so in this case, the index of top at this particular moment in time is 2, right? So the 55 is the top element, and the index of that element is 2. So what is the size of the stack? Well, it's the index of top plus 1, and you can see that this will work. If you think about it, you'll realize this will work in all situations. No matter what the index of top is, if we just add 1 to it, that will give us the number of elements in the array. Sorry, the number of elements in the stack. The array itself might be much longer, but we're only interested in the elements that we have put onto the stack. What would happen though if the array would be empty? In other words, if the stack is empty. So when the stack is empty, we said before that when the stack is empty, the index of top is -1. And so if we add 1 to that, we'll get 0, which is indeed the size of the stack. So it all works out. Let's go back to the code. So again, to get the size, we say return index of top plus 1. Okay, how about is empty? How do we tell if a stack is empty? Well, we just say return index of top equals -1. So when a stack is empty, the index is -1, and whenever the index of top is -1, the stack is empty. So this is a good way of determining whether the stack is empty. Okay, how about push? Remember, we have to, all these methods that we have so far are overriding methods of the stack interface, right? We had the size method, we overrode that, and we gave it a method, we gave it a body, so we implemented the method. Same thing for is empty. Now we're doing push. So how do we insert an element onto the stack? So first issue we have to think about is, what if size is equal to data.length? So for example, let's say the users created an array stack and specified that the capacity, sorry, I don't know why I said -1 there. That shouldn't be there. Let's suppose that the user created an array of created a stack of 7 elements, right, with indexes 0 through 6, and suppose now that we filled it up. So we put, let's say, 11, 22, 33, 44, 55, 66, 77. Okay, so we put in some elements into the stack, and now the user wants to add another element. The only problem is that the capacity of this particular array is 6, right? So let's suppose that the user created a stack with a capacity of 6. Okay, so the size of this array, so the size, if I call the size method, it gives me 7, and that's also the capacity of this array. And so if the user wants to add another item to the stack, it's not possible to do without removing something. So we're not going to remove something without the user asking us to remove something. So what we're going to do instead is we're going to throw an exception. We're going to tell the user, hey, there's no way for me to do what you asked me to do. And so I am just going to throw an exception. So if size is equal to data.length, our data.length is the capacity, it's the length of the array. So if the size is equal to the length of the array, throw new illegal state exception with the message stack is full. And you see here that this method, in the header, it says throws illegal state exception. And in the documentation, it says throws illegal state exception if the array storing the elements is full. All right, now what happens if the array is not full? All right, so let's say we have a situation like this. Let's say we have a situation like this. So we have, let's say, an array of 7 elements with indexes 0 through 6, and we already have, let's say the size right now is 5, right? So we have 5 elements. The index of top right now is 4. Okay. Now suppose I say push, let's say 66. So I want to push 66 onto the top of the stack. So what do I want to do? Well, I first need to increment index of top. I want to get to this node here. Sorry, I want to get to this index, to this element of the array, and I want to put 66 over here. Right. So, but I also need to increment index of top. Now, which one should I do first? Should I first increment index of top, make it go up to 5, or should I first put 66 here? Well, I could really do it in either order, but it makes, I think, more sense to first increment index of top. So make index of top be 5. And then simply put this new element at this index, which is the index of top right now. So put here 66. So how can we implement this in Java code? So we can actually do this all in a single line. You can say data at index plus index of top is assigned E. Now, if you recall, here we're using the prefix increment operator. Right? So when you put the plus at the beginning instead of at the end, it's called a prefix increment. And what that does is it increments T before doing the rest of the statement. So it will increment index of top, and then it will use the new value of this index of top and assign E at that index, at that new index of top. Okay, if we would have done index of top plus, then this would not have worked. Okay, think about why. What would have happened if we would have done data at index of top plus equals E? So it would have still incremented index of top, but it would have done it too late. It would have first put E at the old index of top, which would mean that it would replace the old element that was there before, which is not good. And then it would do index of top plus. But that's not what we want. So anyways, this is what we do. Now we could actually do this in 2 lines, right? So this would be equivalent to first doing index of top plus, and then saying data at the index of top is assigned E. Okay. Anyways, but this is sort of a more concise way of saying it. Okay. How about peek? Right. So the goal of the peek method is to return but not remove the element at the top of the stack. Well, it's quite easy because we have this index of top variable. Right. So first of all, if the list is empty, just return null. Okay. Because there's no element to return. Otherwise, return data at index of top. All right, how about pop method? So again, if the list is empty, if the stack is empty, return null. Then we're going to store the answer in a variable. E answer equals data of index of top, just like we did here in the peek method. But then we also have to remove we have to remove this element that we are going to return. So let's take a look here at the array. Now, until now, I was drawing the array in a not very accurate, not a completely accurate way, mostly accurate, but not completely accurate. So really, what this looks like, what we have really is it's an array of references, right? So this is not an array of ints, for example, or an array of chars. This is an array of E, where E is some reference type. So really, when we have some elements in this array, the elements are not stored, the objects are not stored directly in the array. So the integer, for example, the integer 11 is not stored here. Rather, this element is a reference to an integer object. So here we have an integer object storing, let's say, 11. And suppose, let's say here we have an integer object storing 22. Okay, but again, the object is not stored directly in the array. And although I often draw it as with the 22 inside the array, that's just for convenience because I don't have to draw as much. But the more technically accurate way of looking at it is like this, and now I'll show you why I want to draw like this right now. So let's say we have these three elements in the array, and so the index of top. The index of top right now is 2. And now suppose I want to pop the top element off. Okay, so what I'm going to do here is I'm going to do two things. Well, a few things. First of all, I'm going to store this result in a variable. So I'll say answer, this is going to be my answer. So I'll make answer refer to this variable. And then, I'm sorry, refer to this object rather. Answer is a variable that refers to this object. And now I want to do two more things. I want to say index of top to go down to 1. Right, so until now index of top was 2, but now I'm removing that element. So the new index of top, the new value of index of top is going to be 1. What I also want to do is dereference this object. In other words, I want to remove this reference to the object. Okay, and the way I do that is I set this element of the array to be null. Okay, so in other words, what I want to do is break this link to the object, and I want to make this element have the value null. All right, so let's see how we do this. Now, why am I setting it to null? Because my ultimate goal is that Java will collect this as garbage, right? After we return the answer, I want Java to reclaim this memory, to perform garbage collection on this memory. And so to accomplish this, I'm going to dereference the object. I'm going to remove this reference to the object. Now we still have this reference, the answer, okay? But once we exit the method, this goes away. Right? So once we exit the pop method, this goes away. Because this is a local variable, and so once we exit the method, there will be no variables pointing to this integer object, and so the Java garbage collector will be able to freely delete it. All right, let's see how we do this in code. So again, first we store the answer. Answer equals data is assigned data at index of top. Then we say data at index of top is assigned null. So we dereference the element to enable garbage collection. Right now, the garbage collection will not happen immediately. It will happen only after we return from the method. In other words, only after the answer variable is out of scope. But for now, we're just doing data index of top is assigned null, and then index of top minus minus. So we are removing an element, so the index of top is going down. And then we return our answer, which we stored here. And then once we exit this method, there are no longer any variables, there are no longer any references that refer to the old object that we popped off. And so at this point, the garbage collector will be able to come and reclaim the memory. All right, now just for convenience, we also have a toString method in the ArrayStack class. All right, so this method here is named toString. Notice when I want to print out a stack, I can say something like system.println stack, and Java here calls the toString method for me. Okay, I don't actually need to say .toString. Java calls it for me, but or really, the println method calls it for me. But in order for that to work, in order for that to work well, in order for it to produce a helpful string representation, right? In order for it to produce a representation like what we have here, right? Like this or like this, or what we do is we write our own toString method in the stack class. So here we have public string toString, produces a string representation of the contents of the stack, ordered from top to bottom. So let's actually add in something here. Let's put in the word top here at the top, and let's put in the word bottom here, and let's just show you what it will look like. Okay, so for example, here's a stack containing 6, 9, and 7 from top to bottom, and okay, so that's good. Now, how do we implement this method? So we use a string builder. We've seen this a few times. String builder SB equals new string builder. So we start off by saying the word top, and then an opening square brace. Then we go through the elements of the array from top to bottom. Now, what's the top? That's that index of top, right? So we start int j equals index of top. We keep going as long as j is greater than or equal to 0. And then after each iteration, we do j minus minus to go to the previous element. For each index j, we get data at index j and we append it to the string builder. And then if j is greater than 0, so if j is not the bottom of the stack, we append a comma. So what we want to have is, a comma after each element except for the bottom element. We don't want to have a comma and a space after that. So if j is greater than 0, sb.append the comma and a space. All right, so this is our for loop. It's going to go through the stack from top to bottom and append each element to our string builder. And then at the end, we're going to append a closing square brace and the word bottom to indicate the end of the stack. And then at the end, we'll return sb.toString. All right, so that's really it for the array stack class. It's, again, array stack is an implementation of the stack interface. And this particular class, the array stack class, implements the interface by means of an array. So it uses an array for storage, and then we have the index of top, and that's what we use in this class. Now, here's just an example showing how to use an array stack. So we can say stack of integer stack equals new array stack. Now you could actually say, array stack of integer stack equals new array stack. That works. But there's a benefit in using this, a notation like this, where you say stack of integer stack equals new array stack. And the reason for that is that what you're saying when you say this line, you're saying that I want to use a stack, and I don't actually care too much how it's implemented. Like, my main goal is to use a stack, which, in other words, I want to use something that conforms to the stack interface. Now, I can't create an object of the stack interface, so I have to create an object of some type of class that implements the stack interface. But that detail is not that important to me. What's more important to me is that I'm using something that conforms to the stack interface. And so I know that I can call the push method. I know that I can call the size method. I know that I can call the pop method, because all those methods are in the stack interface. Now, when I actually call those methods, when I actually call the size method or the pop method or the isEmpty method, Java will call the version of those methods that is written in the array stack class, because the type of object that I'm actually working with is an array stack. However, when writing the code, saying stack of integer stack is a way of emphasizing that I don't care too much about the implementation. I'm interested in the stack data structure, whatever implementation. Now, I have to choose an implementation, so I'll just choose array stack. Okay, that's how I think about this kind of line. And so we can push things, so we can say stack.push5. So right now the contents are just 5, and then we can say stack.push 3, and now the contents are 3, 5. So notice the 3 is at the top. The top is at the we print the top at the beginning and then down to the bottom. We can, right, let's see what gets printed here. Right, so here we go ahead and print out the stack. Now, when we print out the stack, as we know, the println method will call the toString method. Which version of toString will it call? Well, obviously, we'll call the one from the array stack class, because that's the type of object that we're dealing with. So we'll call this toString method that we just saw, and that's how we get this string representation: top, and 3, 5, and then bottom. Okay, we can say stack.size, and it outputs 2. We can say stack.pop, and it outputs 3 because that's the top. So it returns 3 to us and it pops it off the top. And right now the contents are just 5. The 3 has been popped off. If we ask, is the stack empty? The output is false, right? So, sorry. Yes, the output is false because the stack is not currently empty. If we pop another element off the stack, now we have an empty stack, and it outputs 5 because that's what got popped off. And then if we ask if the stack is empty, now we get an output of true. If we once again try to pop something off the stack, well, there's nothing to pop off, so the method returns null. It outputs null. All right, and we can push 7 onto the stack, and we can push 9 onto the stack. So now we have, so first we push 7, and then we push 9 on top of that. Then we can peek the top of the stack, so that gives us a result of 9. We can push a 4 onto the stack, so we push 4 onto the top, and we still have the 9 and the 7. I'm sorry, here, this is what we're doing here. And then if we ask for the size of the stack, now we get an output of 3. If we pop an element off the stack, we get 4 because that's the top element, and it also removes it, so 4 is popped off. Then we can push a 6 onto the stack, and then we can push an 8 onto the stack. Then we can pop the stack, so we get an output of 8. And then we can print out the stack, and we have, again, 6, 9, 7. Okay, so we've seen now one implementation of the stack interface, and this implementation uses an array stack. Now let's see another implementation of the array stack interface. So before that, let's just say what is the running time of each of these methods in this class. So the interface doesn't specify doesn't have to specify the running time. In our case, we didn't specify the running time of each method in the interface. But now it would be interesting to know what is the running time of each method in this array stack class, in this particular implementation of the stack interface. So we can see pretty easily that each method does a constant amount of work. So the size method does a constant amount of work, so it's big O of 1. Its running time is big O of 1. Is empty does a constant amount of work. Again, its running time is big O of 1. The push method, okay, so it also only does a constant amount of work. It would not be a constant amount of work if we had to travel through the entire array, for example, right? Then it would be a linear running time. But here we're checking the size. That's a constant amount of work. Comparing it to data.length, we are doing plus index of top, so that's a constant operation, an increment. Then we're accessing an element of the array. So accessing a single element of an array is a constant operation, no matter which index that element is at. We're assigning an element to an array. That's a constant operation. So anyways, we're just doing a constant amount of work in this method, and so we have the running time of big O of 1. The peek method, also constant amount of work, big O of 1 running time. And pop Okay, this is a constant amount of work. Big O of 1 running time. Now the toString method actually is big O of n, right? Because it has to go through the potential. In the worst case, it has to go through the entire array. But actually, sorry, it's always big O of n. Sorry, let me say that more clearly. What is n in our case? It's not really the length of the array. N is the number of elements in the stack. I mean, I guess you could think of it as the length of the array, but it's not really. The number of elements in the stack is a more useful value for n. It's a more useful thing for n to represent the number of elements in the stack, right? As opposed to the number of elements in the array, which we don't really care about necessarily. We care more about how many elements we are actually storing in the stack. Now, this toString method has to go through all of those n elements. So this toString method would be, the running time would be big O of, the running time would be big O of n, okay? But this is not really this is not really an operation of a stack. I mean, you know, it's a method in the array stack class, but it's not one of the methods of the stack interface. But it is interesting to note that it is big O of n. Its running time is big O of n. But we're going to really care more about the main operations. So, you know, size is empty, push, pop, peek. Okay, so all the main operations are run in linear time. So that's a good thing about this array stack class. However, so there is a very important downside to this class, which is that since it uses an array, it has a fixed capacity. Meaning, if I create a stack to hold 1,000 elements, and I add 1,000 elements to the stack, and then I want to push element 1001 to the stack, I will not be able to do that. And we get, the push method will throw an illegal state exception, right, if the array storing the elements is full. So we have this issue, which is when we create an array in Java, it has a fixed size, and that doesn't grow. And so so the point is we might run out of space in our array. So that's a downside to array stack. So a different approach is to use a linked stack. So here we have another class. Public class linked stack implements stack of E. So this is another implementation of the stack interface. And it's the same stack interface that we implemented when we wrote array stack, but now we have another implementation. So we have public class linked stack of E implements stack of E. The main difference between this implementation and the previous one is that here we don't use an array, but rather we use a singly linked list to store the elements of the stack. So we have private singly linked list of E list to store the elements of the stack. Now we don't have to deal with indexes. We don't have to worry about the array running out of space because we're dealing with a linked list, and we can just keep adding elements to the list. Now, recall that, well, what do we want to do with this list? We want to be able to add elements at the beginning. So when we have the push method, we want to add an element to the list. When we have the pop method, or we want to remove an element from the list. Now we could technically, if we want to, use either the beginning of the list or the end of the list for the pop and push. Right? In other words, if we have, if we're building a list here for our stack, right? So we're building a list here for a stack. Let's say we have these, these elements. Let's say we have, 11, 22, 33 in our stack. And suppose we want to add a new element to the stack. So one approach would be to add it at the front. Okay, another approach would be to add it at the tail. And then by the same token, when I want to remove an element from the stack, do I remove it from the front or from the end? So it has to be consistent. So one option number one is to add elements at the front. So if I want to add, let's say, a 44, I'll add it at the front. So I'll make a new node here and add it at the front. And so until now, my head was, the head of the list was here, but now it's no longer here. Now it's here. Right, so that's one approach. And then in this approach, when I want to remove an element, when I want to pop an element off the stack, I'll pop the head of the list off. Okay, so that's one approach. Another approach, though, so approach 2 would be to add and remove from the tail of the list, from the end of the list. So we also have, let's say we also have a tail like this. Now the problem is we happen to be using a singly linked list here. And what's the efficiency of adding and removing at the end of a singly linked list? So to add at the end of a singly linked list, it takes constant time. But to remove from the end of a singly linked list, hopefully you recall, takes linear time. So that would not be great. So I would say approach 2 would not be a good approach, assuming we are using a singly linked list. Right? If we're using a doubly linked list, then we can add and remove from the end without in constant time, rather, right? But we're using a singly linked list, which is slightly more efficient in terms of memory, which is more efficient actually in terms of memory than a doubly linked list. So I'm using a singly linked list, and so I think option number 2 would not be a great idea. It would work, we can make it work, but it would not be efficient to pop elements off the stack, right? Because if I want to remove from the end of a singly linked list, that takes linear time. So the better approach is option 1, where we add elements to the front of the list and remove elements from the front of the list. So now I'm not I'm not going to go through the singly linked list class again, because we've gone through it a lot, and all I'm doing is using that class singly linked list that we've already written. Actually, I'm using even a simplified version of it. So I've removed many of the unnecessary methods. If you take a look here, singly linked list. Okay, this is a simplified version of the one that we had a few weeks ago. Really, I've removed. Anyways, I took away most of the extraneous methods, and we're just using the basic features of a singly linked list. So let's go through quickly now through this class. So to construct an initially empty stack, so we have this constructor, takes no parameters, and we just say list equals new singly linked list. To get the size of the stack, we just say return list.size. Right? Again, list isn't my singly linked list. It has a method named size that gives me the size of the list, so I can just call that method. Is empty. We can just say list.isEmpty. To push an element out of the stack, so remember the approach we're using is to add at the front of the list. So we're going to say list.add first and put the element at the front of the list. To peek, remember if we want to peek at the front of a singly linked list, we have a method named first. It gets the first element but doesn't remove it, so we just say return list.first. To pop an element off the stack, we remove first from the list. And then for a toString method, we say the word top, and then we say list.toString, right? So we get a string representation of the list, and then the bottom. So we get from top to bottom, and that's it. So it's much simpler because we are using the functionality that is built into a singly linked list. And so now what is the running time of these methods? So here we have to remember the running time of these methods for a singly linked list. So because that's what we're using here. So but anyways, here we're using when we say list.size, that's a constant time operation, big O of n, sorry, big O of 1. Okay. Is empty is also big O of 1. Push is also big O of 1, because here we're using list.add first, and if you recall, to add an element at the front of a list, it takes constant time. Here, to peek the element at the front of the list, to look at the element at the front of the list, takes constant time. To pop an element off the stack, what we're doing is we're saying list.remove first, so we're removing an element from the front of the list. This also takes constant time. But again, recall if I would instead do remove last, that would take linear time. So that's why we're not doing it. And then toString, well, this here we're just calling the toString method of the list class. Now this toString method of the list class goes through the entire list, goes through all n elements. So this actually takes linear time, but we can't really do better than that, right? If we need a string representation of a stack, we can't do better than big O of n, because we automatically have to go through all n elements in order to get the string representation. So there's no way of avoiding that. And so we can't do better than big O of n. But the point is, for all the other operations, for the main operations of singly linked list, I'm sorry, of this linked stack class, they all run in big O of 1 time. So the same big O of n, the same big O running time as array stack, but one big benefit of linked stack as opposed to array stack is that there is no fixed capacity. And we can because we're using here a singly linked list, and we can just keep adding nodes to the singly linked list, until we run out of memory, basically. But the point is, we're not dealing with an array of a fixed size like 1,000. Okay. Now, for using this, if we want to use this linked stack class, so we already saw an example of that. I'm sorry. Here we have the example I showed you earlier where we're using our stack. So I said stack of plate stack equals new linked stack, or stack of integer stack equals new linked stack. And then I pushed elements on and popped them off and so on. Again, I could say linked stack of integer stack equals new linked stack, but it's a little bit nicer to say just stack of integer stack. The point is, I'm using a stack. I don't really care about the implementation. And so good. So that's how we use these two classes. So just to what we just saw is two implementations of our stack interface. We saw array stack, which stores the elements in an array, and linked stack, which stores the elements in a linked list. Now, Java has its own built-in stacks. So in other words, we didn't actually have to write the stack interface and the stack classes that we just wrote, the array stack and the linked stack classes that we just wrote. We didn't have to write them. What was the benefit of writing them, though? Well, they helped us see how stacks work, right? If we wouldn't have written them, we would have known how to use stacks, but we wouldn't have known how stacks can work internally. So we saw two different ways that stacks can work internally. However, we didn't, as I said, we didn't actually need to write all this ourselves. We could really just rely on Java's stack class. Okay, so let me show you an example of that. So again, remember the operations that we had in our interface are size, is empty, push, peek, and pop. Those same operations are all available in a class named stack that is built into Java. So here's an example. Here we are using, notice we have import java.util.stack. So stack is a class in the java.util package. I mean, create a stack by saying something like stack of integer stack equals new stack. Okay, now we'll come back to these two lines in a little bit. But we can say stack of integer stack equals new stack. And then we can just do exactly like what we did using our stack. We can, say stack.push I, push elements onto the stack. We can print out the stack, which will give us a string representation of the stack. We can push more elements, another element. We can peek. We can say stack.peek. We can say stack.pop. We can get the size of the stack. We can check if the stack is empty. We can pop from the stack, and we can print out the stack. We can do all the things that we did with our own stacks, but we can do this using the built-in Java stack. So again, Even though this is named stack, which is the name of our interface, that's not what we're referring to here at all. Here we are simply referring to a class named stack that is built into the Java API. It's in the java.util package. Let me just run this quickly. Okay, so here we see we are pushing, 5, 6, 7, 8, and 9. Now, very interesting. When we print out the stack here, it prints it from bottom to top, unlike the way we were printing it in our versions of the stack class, right? So here, when we use our version of the stack class, if I run this, just going back here, we're using our version of the stack class, where we're using stack of plate stack equals new link stack, but it would be the same for array stack. Notice here we print from top to bottom, okay? But Java stack, when you get a string representation of Java stack, it's from bottom to top, which is a little annoying. But we're going to see that we're going to actually not going to be, we're going to prefer not to use the Java stack class. We're going to use a better alternative that is also built into Java. And that alternative approach will give us a string representation in a standard way, meaning from top to bottom. But again, right now I'm using stack of integer stack and equals new stack. So I'm using the stack class that's built into Java, and its toString method gives you a string representation of the stack from bottom to top. So I'm sorry, from bottom to top. So here we have 5 at the bottom of the stack. 5 was the first thing that was pushed onto the stack. Remember, here we have pushing 5, and then 6, then 7, then 8, then 9. So 9 is at the top of the stack. It gets printed at the end. Okay, that's just a quirk of the stack class that's built into Java, but we're going to try to avoid using it, and I'll talk more about that. Okay, so we can push 7, and then we see that we have 7 at the end, pushed onto the stack. Then we can peek, we get 7, we still have the same stack. We can pop 7 off the stack, and now we have 7 has been removed. We can get the size, it's 5. We can pop 9, 8, 7. Right, so we notice when we're popping from the top, 9, 8, 7, 6, 5, and then now the stack is empty. Okay, so here, this is using Java stack class. Let's look at the documentation for the stack class. Right, so as usual, to get the documentation, you say something like stack Java, and then I want version 17. That's one of the latest versions. And so here we have the documentation. So we see class stack of E. It's a generic class, and it says the stack class represents a last in, first out stack of objects, right? So we know what that means. We know what LIFO means. That's the approach we've been using all along for stacks. It says, the usual push and pop operations are provided, as well as a method to peek at the top item on the stack, and a method to test for whether the stack is empty. And then some more stuff. When a stack is first created, it contains no items, okay? Just like what we did. But then here's a very important note. A more complete and consistent set of LIFO stack operations is provided by the DEC interface and its implementations, which should be used in preference to this class. So it's saying, basically, don't use this class. So this class, if you see here, has existed since version 1 of Java. And back then, there were very few data structures built into Java. For example, there were no array lists. There was something called vectors instead. But they weren't the data structures that were built into Java, like stack and vector at the time, were not implemented in ways that we like to do nowadays. They had certain quirks and certain things that nowadays we don't think is great, but they haven't been removed from the language. They haven't been removed from the Java library because there's tons of code that relies on this. There's tons of code that's been written for the past 25 years or so since Java has existed, or 27, 28 years by now probably. Anyways, there's tons of code in existing code bases that use the stack class, that create an object of the stack class and use it. So they don't. This class has not been removed, and it's likely never to be removed from the library. However, there is a note here for users saying, if you're writing a program now, a new program, you should prefer to use the deck interface and its implementations instead of the stack class. Okay, but there's nothing really terrible with using the stack class. People use it all the time, but for whatever reason, the designers of the writers of this documentation, and probably this is a more widespread view among Java experts, is that we should use deck instead of stack. So, but we could use stack, and if you see here, there's a constructor, and there are methods like empty, peek, pop, push, search. Okay, we don't even know what search is. That we'll ignore that. There's also a method named where is that? Is empty, that is inherited from a superclass. So if you noticed in the code that I wrote using Java stack class, I didn't say empty. I said is empty. I could have said empty. Let me show you what I mean. Right, so here when I say, when I want to know if the stack is empty, so I say while not stack is empty. Okay, so stacks have this method is empty, which they inherit. I could also just say empty. That's using the method that's built into stack itself. But anyways, I just used is empty to be more consistent with our stack interface. At any rate, following the documentation, we're going to try to avoid using the stack class. And here's the better approach. Okay, this is from the documentation. Remember, it said a better approach is to say something like deck of integer stack equals new array deck of integer. Okay, now actually, sorry, this word integer here is actually optional, as you probably know. You can leave it out. So that's what I did as well. So I just said deck of integer stack equals new array deck. Now we should take a look now at the deck interface. So notice the documentation said deck is an interface, and then array deck is an implementation of the deck interface. So we cannot create a deck directly. We cannot say new deck. Okay, because deck is an interface, but we can say new array deck because array deck is a concrete class that inherits from the deck interface. And we can use it exactly the way we used it before. I don't have to make any other changes to the code. In other words, I can call the same push methods, the same push method, the same peek method, the same pop method, the same size method, and the same is empty method, all as I expect to have with a stack. So even though this is called a deck and it's not called a stack, we are using a deck as a stack. Now we'll see later, not in this video, but next class, what exactly a deck is. A deck is a more general thing than a stack. A deck includes all of the stack operations that we like to use, but it also includes some additional operations. But we'll see more about decks next class. Let me just show you what the output will look like. So remember when we were using Java's built-in stack, this is the output from before. The toString method gave us the string representation of the stack from bottom to top. The more standard way, apparently nowadays, is to have from top to bottom, and that's the approach we used in our link stack and array stack classes. So let's take a look at what happens when I rerun the program. Now we're using deck instead of deck and array deck instead of stack. Okay, so it's rerunning. Okay, here we go. So now you see the elements are their string representation has the elements from top to bottom, which is the way we did it in our link stack and array stack classes. So this is more consistent with how we implemented stacks. Anyways, but notice the rest of the stuff works exactly as before: pushing, popping, peeking, and it all works as we expect. Let's go back here, and I want to go to the deck interface. Okay, so here we have interface deck, deck of E. E is the type of elements held in this deck. Now, we know we cannot create an object of the deck interface. An interface cannot be instantiated. So whenever we look at an interface, or usually when we look at an interface, we are looking for classes that implement that interface. So here we have a list of all known implementing classes, meaning all the classes that the Java library has that implement the deck interface. And there are 4 of them. The 2 middle ones are more fancy they have special features that are not relevant to us. The 2 that we are interested in is ArrayDeck and LinkList. So these are 2 different classes. They're very different classes, ArrayDeck and LinkList, but they're both classes that implement the deck interface. So any method that is specified in the deck interface will have to be implemented by ArrayDeck and also will have to be implemented by LinkList. So in our case, we use ArrayDeck. We could have also used LinkList. Okay, so let me show you. Another option would be to say we can use we can say deck. So let me comment this out. We can say deck of integer stack equals new linked list. Sorry, no. Linked list. Okay, and then let me run the code, and it's gonna all the rest of the code. I can call the push method. I can call the pop method. I can call the peek method. I can call is empty. I can call size. All of this runs as we expect. Right, the toString method gives us a string representation from the top to the bottom, as we've come to expect, and everything works as before. Right, so we can use any implementation. We can use ArrayDeck. We can use LinkList. I'm going to stick with ArrayDeck. I think my impression is that ArrayDeck is a little bit more efficient than LinkList. Not 100% sure about that, but so really either one is fine. There's not much difference in efficiency. It's a small difference, perhaps, a small benefit, perhaps, in ArrayDeck. At any rate, though, let's go back to the deck interface. Okay, so we have so we'll just read a very little bit. So a deck, it says it's a linear collection that supports element insertion and removal at both ends. So this is more general than a stack, right? A stack we can only add and remove at the top or the front of the stack. Here, a deck technically allows us to insert and remove at both ends, but we're not going to use it in that way, at least so far. For now, we're just using insertion and removal at the front. In other words, at the top of the deck. All right, so the name deck is short for double-ended queue. Okay, we'll learn about what double-ended queue means next class, and it's usually pronounced deck. Okay, so this is helpful because it's not obvious how to pronounce this word. But anyways, the way it's usually pronounced is deck. And then here they give you a summary of deck methods. So remember that decks allow you to add and remove both at the front and at the end of the deck. So this line is insertion, and then the next line is removal, and then the next line is examine. So examine is like peek, right? Just tell me what's there without removing it. So to deal with the first element, or the head, or as we would call it, the top of the stack, right? That's equivalent to the first element. So we can use add first or offer first. Now, what's the difference between these two methods? Well, the add first method throws an exception if there is no more room. and offer first, instead of throwing an exception, would return a special value. And then remove first, if there are no more elements left, it will throw an exception. Pull first is a similar method. It will, but instead of throwing an exception, it will return a special value, null in this case. And then examine, same idea. Either will get first would throw an exception if the deck is empty, but peek first would, instead of throwing an exception, would return a special value if the stack is empty. And the same idea for getting, for inserting or removing or examining the last element. But we're not going to be dealing with that yet because we're not dealing with decks in all our methods yet. Right now, we're only dealing with, inserting and removing from the front. Okay. Now, they talk more about as follows. They say decks can also be used as LIFO, last and first out, stacks. And they say this interface should be used in preference to the legacy stack class. Okay, when they say legacy, they mean something that has existed for a while and it's not really great anymore, but it exists for a while. Usually it also implies that it's not that great anymore, but we can't get rid of it because it's so important and it's used so widely. But they're saying for now we should prefer to use decks instead of stacks. When a deck is used as a stack, elements are pushed and popped from the beginning of the deck. And they say stack methods are equivalent to deck methods as indicated in the table below. So this deck interface, in addition to having add first, remove first, and get first, which we can use, it also has methods that are specialized for stacks: push, pop, and peek. They're equivalent to add first, remove first, and get first. Okay, so push, same thing as add first. Pop, same as remove first. Peek is the same as get first. But we don't have to think about first, and we don't have to think about that. We can just use the standard stack operations: push, pop, and peek. All right. Now, one more thing I wanted to say here. Let's go back up to these two classes that implement the deck interface. So again, the deck interface doesn't provide an implementation, but the implementation comes from any of these classes. So array deck implements the deck interface using an array. Linked list implements the deck interface using a linked list. So in many ways, they're similar to the array deck is similar to array stack, and linked list is similar to linked stack. Okay, they're actually, now these two classes are much more sophisticated than the ones we wrote, much more complicated, have much more functionality, but the basic idea is similar. Now, you may wonder, when we talk about array deck, is it like our array stack that has a fixed capacity? In other words, remember we talked about when we create an array stack, the user specifies the capacity, or we use a capacity of 1,000, but that's it. Once we create the array stack, it has that capacity forever. Is it the same for array deck? The answer is no. The very first words of the documentation say resizable array implementation of the deck interface. Array decks have no capacity restrictions. They grow as necessary to support usage. Okay, so the point is that there is no fixed capacity. There is no capacity restriction for array deck. Now you may wonder how it actually does this. If it's using an array, how does it grow that array? Okay, well, we'll learn about technique for doing that in about a week or two. But for now, we just note that this array deck class, which is built into Java, it provides a resizable array implementation, and it grows as necessary. Now I believe I showed you how to use JShell before, but when you're learning about a new built-in data structure, or any new feature in Java, and you want to quickly test a few quick examples, it's very nice often to use JShell. So let me show you how we can use it. So here I'm going to use it on my computer here, but then I'll show you that we can do the same thing in Replit. So here I'm working at a shell on my laptop, and what I'm using right here is called Git Bash. This is a Windows computer. Windows does not come with the built-in functionality that that a Linux command line has. What many people like to use in Windows is something called Git Bash, which gives you a lot of that functionality. But you don't really need to use it. Anyways, you just need to be able to use JShell, and you just run the JShell command, and now you can say something like, dec of integer, let's call it stack equals new array dec. Okay, so we see here stack is currently empty. We can say stack dot push. We can push, let's say, 11 onto the stack. We can say stack dot push again, push 22, say. You can say, we can even have a for loop here. We can say for int I equals 0, I is less than 4, I plus plus, and we can say stack dot push I. Okay, now let me go ahead and print out the stack. Okay, so we see here 11 at the bottom. That was the first thing we pushed. Then 22, then 0, 1, 2, and 3. We can say stack dot peak. Oops, stack dot peak. And we see 3, that's the top of the stack. If we print out the stack again, we see the 3 has not been removed. If we say stack dot pop, it has popped 3 off the stack. And now if I print out the stack, the 3 has been removed. We can say stack dot size, and it's 5. That's how many elements there are right now. We can say while not stack dot is empty, stack dot, let's say system dot out dot print line stack. Actually, do I need to say that? Not sure. Let's just say stack dot pop. Okay, so it didn't print it as was popping, but let's print out the stack now, and it's empty. Okay, anyways, I can push a new element on, say stack dot push 66, stack dot push 77. We can print out the stack. Anyways, so this is a nice thing to use when JShell is a nice thing to use when you're trying out a new feature in Java. Now I will also show you that you can use JShell in Replit. So if you aren't sure how to use the command line on your computer, well, first of all, I would encourage you to learn about it. But if you really don't want to, you could just use Replit, and Replit has a built-in command line, and JShell will work there just fine. So I'll show you that quickly. All right, so you can, let's just zoom in here a little bit. So we can close this, make more room here. So here we're working in what they call the console. You can also work in the shell. Will work the same. So you start by saying JShell. Okay, it's a little bit of initialization that it has to do, and then we're off and running. So let's see. Taking a little bit of time there. Okay, here we go. So we can create a stack. can say stack. Sorry, we can say, just like we did before, we can say dec of integer stack equals new array dec. And we can say stack dot push. Whoops, sorry. I have to push an element, let's say 88. Okay, stack dot push. Let's say 22. Whoops, typo. Okay, let's print out the stack. Okay, anyways, that's a cool little tool. JShell is a cool little tool. I've showed it to you before, but just wanted to show it again. So just to recap what we just did, we've talked about using Java's stack class. We've talked about using Java's dec as a stack. So we talked about the dec interface. We talked about two concrete implementations of the dec interface, namely ArrayDec, which uses an array internally, similar to our array stack, but this array grows as necessary, right? So it's not limited to a size. Linked list is another implementation of the dec interface, and this implementation uses a linked list internally, similar to our linked stack. And that's yeah, okay, so that's what we just talked about. Next thing we're going to talk about, and this is the last major thing we're going to do here, is talk about different nice applications of stacks. So we're going to see 4 different applications. One is reversing an array. Another one is determining whether a stack's elements are consecutive. Another one is matching delimiters. We'll see what that means. Another one is matching HTML tags, and we'll see what that means. That'll be in a separate video.